Hello, welcome back. So I'm not sure if Nathan will be joining us today, but I think it's time to get started nonetheless. So we had a few homework problems. We had these three problems, these three functions we were given in our last class, and we were going to find the derivatives. So I want to see if any of you guys were able to find the derivatives of these functions. Just type it into the chat if either you have an answer or to let me know if you weren't able to find the derivatives. Just interested to see if you guys were able to do these problems. All right, sure, no problem. Let's review these. So this might be a bit of new vocabulary. The word differentiate and differentiate the following function, that just means take the derivative. So whenever you have a question that asks you to differentiate a function, they're just asking you to take the derivative. So let's take the derivative of f of x. We have f prime of x is the notation for the derivative. And we want to use not only the power rule, but we also want to use the product rule as well, because we have a first function and we have a second. So if we call this first function u and we call the second function v, then the derivative using the product rule is going to look like this. We have to take the derivative of the first, so that would be u prime, and then multiply that by the second function. And then from there, we want to add that to the first function times the derivative of the second. So that would be v prime. So we have u is 3x squared to the 3/2 power, or just 3x to the 3/2 power. So we want to use the product rule to find the derivative, or the power rule is what I meant to say. So u is 3x to the 3/2. And then we have u prime is going to be, well, we want to take the exponent and then multiply it out front. So we're going to have 3/2 x, and then 3/2 minus 1 is just 1/2. So this would be 3/2 to the x times x to the 1/2 power. So that would just be 3/2 times square root of x. X to the 1/2 is just the square root function. So we have 3/2 times square root of x times v, which is sine of x. All right, so we're halfway there. We have to find two terms, and we've already found one of the two. Next, we just have to find our v prime. So if v is sine of x, then that means v prime is going to be cosine of x. That's just the derivative of sine, which of course is cosine. So this would be 3/2 square root of x times sine of x plus the first function left alone times the derivative of the second, so times the cosine of x. All right, and that's it. That is our derivative. We have differentiated f of x, and we got f prime of x, this function right here. So now let's go ahead and do the same thing for g of x. So g of x is square root of x times e to the x. So we want to use the product rule once again to find g prime, to find the derivative. So we can write this as x to the 1/2 times e to the x. And it makes it a little bit easier to have it as x to the 1/2 instead of e to the x, because it's very clear from this point on how we take the derivative. We know exactly what to do when we have an x to some power. We know exactly how to take the derivative of that. So we have g prime of x. We're going to apply the product rule once again. We have a u and we have a v right next to it. So it's going to be u prime times v, which would be 1/2 x to the negative 1/2. Times our second function, which is e to the x. And then we have plus the first, so x to the 1/2, times the derivative of the second. And we went over this briefly last time. E to the x is really an interesting function because it's the only function that when you take the derivative of it, you get the same thing back. The derivative of e to the x is e to the x. So this would be our answer right here. This is the derivative of g of x. This is g prime of x. And then I want to clear the screen before we do h of x. Oh, yeah, sure. I'll show that right now. So I see in the chat you would like to maybe discuss why this is negative 1/2. So let's apply the product rule to u. So we have u is going to be x to the 1/2. So the product rule shows us that whenever we take the derivative of something like this, we have to multiply the exponent out front. So this would be 1/2. And then our new exponent is going to be 1/2 minus 1. Remember, with the power rule, we always have to subtract 1 from the exponent. So in this case, we're going to subtract 1 from our exponent of 1/2. So we want to simplify this a little bit. 1/2 minus 1 is negative 1/2. So we're going to get 1/2 x to the negative 1/2. So that's where that negative 1/2 exponent comes from in our derivative of g of x. So another way we might want to write that would be as a reciprocal. Instead of using a negative exponent, it might be better just to rewrite this as 1/2, and then x to the negative 1/2 is written as 1 over the square root of x. I feel like it's a neater and a nicer way of expressing the same information, the same derivative. It's just usually preferable to use a root instead of an exponent when possible. So this is going to be, if we condense the fractions into 1, we're going to have just 1 over 2 square root of x. And then, of course, we had e to the x. And then the second term, we remember that is just going to be u, this is going to be u and then v prime. So this is going to be, well, we can write this as u to the 1/2 for u, but I might just put square root of x instead to make it look a little bit nicer, a little bit neater. So we have square root of x times e to the x. And like I said before, if you wanted to just leave it like this is technically correct right here. It's correct in value, but if you were to see a problem like this on the AP exam, they would probably just have you use a root. Like I said, it's just nicer and neater. So this is g prime of x. So before we go on to h, I think I want to clear the board. I think we're going to need a little more room to do this one because it's a little more tricky than the other two that we've been working on so far. And don't worry, I'm video recording this lecture. So if you guys want me to email it to you for review to study it, I'd be more than happy to do that in case you missed anything. So we have h of x is equal to the natural log of x divided by x squared. So there are a few different ways we can approach this one. We can either use the power rule, or the product rule, which of course we would make it something like this. We can make it maybe x to the negative 1/2. Actually, I want to put it in exponential notation before playing around with reciprocals. So we can call it natural log of x, and then this would be over x to the x to the positive 1/2, excuse me, and then this would be natural log of x, and then we're going to make this into a negative 1/2 and move it to the top instead of on the bottom of the fraction. So this would be times x to the negative 1/2. And To be honest, there are two different ways we can do this using the derivative rules we learned in the last lesson. There's this way, and then there's a slightly easier way, but I want to show you guys this way first. So of course, we're going to use the product rule just like we've been doing so far. Ru is equal to natural log of x, and then Rv is equal to x squared. So let's recall what the derivative of the natural log of x is. And I want to remind you that this is just one of the ones you want to remember after a while. Kind of like all the trig functions. They have a really specific, each of them they have a really specific derivative. So this is one you just want to commit to memory as soon as you can, because it's going to come up constantly throughout this class and throughout math classes after this one as well. So the derivative of natural log is 1 over x. So if u is natural log, u prime is 1 over x. And then if v is x squared, then v prime is going to be 1/2 x to the negative 1/2, or like we saw in the last example, it's better if we just make this 1 over 2 square root of x. And this is another one that's going to come up pretty frequently just because the square root function is a really common function. It's a good idea just to remember that the derivative of the square root function is going to be 1 over 2 square root of x. Just like the natural log, this is going to come up quite a bit. So let's go ahead and apply the product rule for this. We're going to have h prime of x is u prime times v. So this would be 1 over x, that's our u prime, times our v, which is square root of x. And then we have that plus our second term, which is going to be u times v prime. So u, of course, is the natural log of x. And then we just found out that v prime is 1 over 2 square root of x. 1 over 2 square root of x. So we have v prime, and our u is right here. So that's one way we could do it. But I want to show you guys another way. And actually, I meant for this to be kind of a segue into the next technique we're going to learn about. So far, we've talked about the constant rule for derivatives, and the product rule, and the power rule. The next one we're going to be learning about is the quotient rule. And I want to just get this out of the way. We don't really need this anymore. We're going to be working with the same function. But I want to give you guys just a quick definition of the quotient rule before we go any further. The quotient rule says that if you have some function, f of x, as a fraction, say we have just in a generalized form, say we have u divided by v. U is a function and v is a different function. The quotient rule says that the derivative of this is going to be the derivative of the top times the bottom. So that would be u prime times v. And then this time we're going to do a subtraction. With the product rule, we used addition, but with the quotient rule, it's going to be subtraction. It is u prime times v minus the top function times the derivative of the bottom. So that would be minus u times v prime, all over the bottom squared. So this would be over our function v to the second power. So let's apply this rule to find h prime of x. So u is our top function, v is our bottom function. So we have the derivative of the top. So of course we remember that's just 1 over x times v, so square root of x. And then we have minus the top function times the derivative of the bottom function. And the bottom function is square root of x, so the derivative is 1 over 2 square root of x, all over the bottom squared. And then from here we can simplify a little bit. You might be tempted just to go ahead and make this whole thing into just x, because square root of x to the second power, of course, that eliminates the radical. But in this case, it might be easier just to simplify first and then deal with whatever is left. So what I mean by that is maybe splitting up into two terms, and then it might just be a little bit easier to simplify that way. So h prime of x is 1 over x square root of x. And then I'm going to call this 1 over square root of x squared. And then we have minus natural log of x times 1 over 2 times the square root of x times the same thing. I'm going to make this another 1 over square root of x to the second power. And it just makes it a little bit easier to deal with because we have 1 square root of x right here. We have 2 of those in the denominator. So one of these is going to cancel with this one entirely. So now all we have is just 1 over x square root of x minus, this would be, well, in this case, it might actually be better just to make this 1 over x, but for the first term, as you can see, it worked out better to do it this way instead. But for the second, we're going to make this just 1 over x, so we have natural log of x, and then our denominator is going to be 2 root x times x. And this does look a little bit different than the last one. It's because the conventions we use for these different derivative rules, and they give us something that's kind of in a different form than what we're used to. For example, we could make this look a lot more like our last answer if we were to maybe combine the x's together. We can make this x to the first power, and then we can make this one into x to the 1/2, and then we could combine exponents, but it doesn't really matter. This is equal in value to the derivative we got in the last time we did this problem. Same problem, different method. The answer is the same in value, even if it looks different. All right, so that is the quotient rule. So I think we're going to do a bit more practice with the quotient rule. It's a little more complicated than the other ones we've learned so far. So we're going to just practice it a little bit more before we move on. So let's say we have the function 3 minus 1 over x. Oops. And then we have this divided by x plus 5. And we want to differentiate this function. We want to differentiate f of x. Find the derivative, find f prime of x is what we're trying to do here. So for the quotient rule, we want to just recall how that rule works. We have to do the derivative of the top times the bottom. So we're going to start with that. So the derivative of the top would be, well, let's maybe just assign u and v real quick. V is the denominator. So let's find u prime. So of course we remember the derivative rule for a constant is just the derivative becomes 0. The derivative of 3 is just 0, so we have 0 minus, and then we have negative 1 over x. So we could apply the quotient rule to this one as well, but I think it's better if you just remember this one, kind of like the same way we remember the other special derivative cases, like the trig functions, for instance. The derivative of 1 over x is negative 1 over x squared. So if we were to take this derivative, we would get negative 1 over x squared. And then as you guys can see, we don't even really need to keep the 0 there. It's useless. So I want to rewrite this, make it u prime is just positive 1 over x squared. Negatives cancel each other out quite nicely. And this is our derivative. This is our derivative of the numerator, derivative of u. Now we have to do the same for v, and v is a lot easier. Well, the derivative of x is always just going to be 1. If it's just a plain variable with no number being multiplied by it, the derivative is just 1. And of course, derivative of 5 is going to be 0, just like the derivative of 3 was. So we have everything we need. We have a u, we have a v, we have a u prime, and we have a v prime. So we're going to make this the derivative of the top times the bottom. So this would be 1 over x squared. I want to put that on top. U prime is right here. Times the second, times the bottom. So this would be times x plus 5. And I'm going to move some of this aside real quick. We're kind of running out of space. So I'm going to move the u prime over to this side of the screen. And this is v. And then we're going to subtract u times v prime. So we're going to make this 3 minus 1 over x times v prime, which is just 1. We don't even really need to put that. But then that's going to be all over v squared. So v squared is going to be x plus 5 squared. So if we were to expand this, we would make this into x squared plus 10x plus 25. But in this case, I'm not really all that concerned about expansion. That's not really necessary. For this one, I think I might actually just leave it in this form, x plus 5 squared. And the reason why this is a little bit better is because if you wanted to split it up and simplify it in the same way we did the last problem, make them two separate denominators, two separate fractions, it would work out pretty well. This x to the 5th right here would cancel with one of these x to the 5th. Or sorry, I said x to the 5th. I meant to say x plus 5. So this one on top would cancel with one of these we have on the bottom. So that's why I don't really care that much about simplification and expansion right now. The main thing we're trying to practice here is the derivative itself. Quotient rule is the most important thing at the moment, so it's not really worried too much about simplifying. Moving on. So next, we want to use the quotient rule, and I thought this was kind of a cool example. We're going to use the quotient rule to prove the derivative of the tangent function. So just a quick refresher. The derivative of the tangent function, tangent of x, is secant squared of x. And this is just another notation for derivatives. We could just call this y prime would be tangent of x, so then, sorry, y would be tangent of x, so then y prime would be secant squared of x. That's one other notation we can use, or we might do what we've been doing up until now. We could have f of x and f prime of x, but my point is there are just a lot of different notations we can use. ddx or dy dx are just conventional notations for the derivative. So let's go ahead and prove this. So if our function we're given is tangent of x, let's go ahead and find the derivative using the quotient rule. But we have to rewrite it first. We have to rewrite it in a certain way so that the quotient rule can actually be used. We have to recall some of those trig identities we might not have seen in a while. We want to recall the fact that the tangent function can be written as sine of x over cosine of x. So we have that. So now we want to apply the quotient rule to this function. We want to find f prime of x. Our top function is u, bottom function is v. So the derivative is going to be the derivative of the top times the bottom. Derivative of the sine function is just cosine. So we have derivative of the top times the bottom. And then we have minus the top times the derivative of the bottom. The derivative of cosine is a negative sign. All over the bottom squared. And at first glance, it doesn't really seem like it makes that much sense. How could we get a secant squared from something as complicated as this with a bunch of different things going on? So this is where we have to simplify things. I want to start by taking the numerator and making this first term into just cosine squared of x. And then I want to do the same thing for the second term. So notice how we have two minus signs. So they're going to cancel out and they're going to become positive together. So this is going to be plus sine squared of x. And then we have cosine square root of x on the bottom. So I know we don't really care that much about simplification, but in this example, it's essential to simplify it, just so we can understand where the derivative of tangent really comes from, to understand exactly how we could get secant squared as the derivative of tangent. So let's recall some of those trig identities. There is a Pythagorean identity that tells us that the sine squared of x plus the cosine squared of x is just going to be 1. So our numerator becomes a lot simpler. It just becomes 1. We have 1 over cosine squared of x. And then we want to use one of those reciprocal identities to simplify this further. The reciprocal of sine is cosecant, and the reciprocal of cosine is secant. So this is just going to become secant squared of x. So I don't know if you agree, but I thought it was a pretty cool way of proving why this derivative is what it is. They just use the quotient rule and a few of the trig identities to simplify. Now let's see what else we have going on. So I want to give you guys an example to practice. Let's say we have the function f of x is 3x squared plus 5x, and then we have that divided by 2 times e to the x. I want you both to take a few minutes and try this. I want you guys to find the derivative of this function using the quotient rule. And in case you want to have the formula for the quotient rule open, ready for whenever you need it, it is on page 120 of the book, and I'll write this on the board as well. All right, so both of you give this a try, and let me know if you need any help. And when you have an answer, just go ahead and type it into the chat. All right, so let's review this. So of course, we want to start off by identifying u and v. So of course, v is always going to be on top. And u is on top, and then v is on the bottom. So now we want to find u prime, and we want to find v prime. So derivative of u is going to be, we want to apply the product rule here. We want to take 2, multiply it out at the front, and then of course, using the power rule, our 2 becomes a 1. Our new exponent is just going to be 1. We have 6x to the first power when we apply the product rule. And then the derivative of 5x is just going to be 5. Whenever you have a constant and a variable and you take the derivative is always just going to be the constant without the variable, as long as it's to the first power. It wouldn't work if it were to any other power but 1. So that's our u prime. And then v is going to be, well, we can apply the product rule for our denominator to find the derivative of 2 times e to the x. So that's going to be the derivative of the first, which is 0, times the second, plus the first, which is 2, times the derivative of the second. So this is just going to be 2e to the x. Derivative is the same as it was before because it's that interesting property of e to the x that makes it so. So we have the derivative of the top times the bottom. So this would be u prime times 2e to the x minus the top times the derivative of the bottom, which of course is still going to be 2e to the x. All over the bottom squared. So let's simplify just a little bit. Like I said, we don't want to emphasize it too much because we care about the calculus itself, but it might be helpful just to make this into 1 because we can cancel both of these 2e to the x's with this 1 on the bottom. So if we eliminate this one and eliminate that one, this is going to become just to the first power. So this would be 6x plus 5 minus, and then if we were to distribute the negative sign to both of those terms, we would make it 3x squared, no, minus 3x squared minus 5x. Forgot the 5. Minus 3x squared minus 5x. And then it's just going to be 2e to the x. And then, of course, we can simplify it further, but I think there are more important things to talk about. So we have talked about the product rule, the power rule, the quotient rule, and the constant rule. So there is just one more of these rules we're going to learn today that will kind of round up our understanding of the derivative of a function and how to take the derivative. So we're going to start with the chain rule. And if you've ever talked with someone who is maybe in a calculus class right now or who's taking calculus, you might know that the chain rule has a fair bit of notoriety. It's a lot more complicated than the other rules that we've talked about thus far. So notice how each of these rules can be applied in certain situations. Of course, quotients apply to fractions, power rule applies to exponents, so on and so forth. The chain rule applies whenever we're trying to take the derivative of a composition of functions, and I want to type that up as well. And remember that a composition of functions is just a function of another function. So I want to maybe give just a brief definition of this rule and then do some practical examples to help understand it better. So if we have f of x, and I'm still going to use u and v. They are pretty useful in this context. So I want to make this, instead of u times v, we're going to make this u of v. So u is the outer function, and then v would be the inner function. So then the derivative of this would be u prime of v times the derivative of our inner function. So that would be times v prime. So I want to illustrate this with an example. Let's say we have the function sine of x squared. We can tell it's a composition of functions because clearly sine would be our outer function. And clearly x squared would be our inner function. X squared would be v in this situation. So we want to apply the quotient rule and find the derivative of this function. Or I keep saying quotient rule. Don't know why. I meant to say chain rule. Sorry about that. We're going to use the chain rule to find the derivative of this. So going by this definition, we have to ignore v, first of all. We want to just find u prime. So if u is sine of something, for now we're going to just pretend it's sine of x. So of course, u prime would be cosine of x. So we're going to make a cosine of something. The definition says we want to make it the derivative of the outer function and then leave the inner one alone. So we're not going to do anything with the x squared. We're going to just leave that alone. And then we want to multiply it by the derivative of v. So if v is x squared, v prime is going to be just 2x. And that's it. The derivative of the sine of x squared is going to be cosine of x squared times 2x. And that's how we use the chain rule to find the derivative of a composition of functions. So let's do some more examples. I found that with most of my students, it takes a few different iterations of this to understand it completely. It's definitely one of the more difficult derivative rules we learn in this class. So let's go back. I'm going to go to page, let's see here. I'm going to go to page 134 in the book. They have some pretty good examples of using the chain rule. So let's say we have a function, let's say we have natural log of 3x squared. And we want to find the derivative. So the derivative of y would just be y prime. So we want to use the chain rule. And the thing that kind of gives that away is because we have a clear outer function and we have a clear inner function as well. So u is the natural log function, natural log of v. So then ignoring this v, we would make this, let's just pretend it's an x for now. Because now we can approach it like this. We know the derivative is just going to be 1 over x. And then we have v is 3x squared, so then v prime is going to be 6x. So we are going to just use the chain rule again. So we're going to have the derivative of the outer function, 1 over x. But instead of an x, we're going to put the inner function in there. And then we're going to multiply that by the derivative of the outer function. We're going to multiply that by v prime, which is just 6x. So this is u prime of v, and this is v prime right next to it. So we could simplify this a little bit. We could just put this as one fraction. Of course, 6 over 3 reduces to 2, and then x over x squared is just 1 over x. So 2 over x would be the derivative in this case. So let's try a few examples. I'd like for you guys to try this out on your own. So let's say we have the function g of x is, what would be a good one? Maybe we have g of x is the square root of 2x cubed plus 3. I'd like you guys to try this one on your own. Use the chain rule to find the derivative of g. And I want to just put the rule back up there, the general definition for the chain rule. All right, give it a shot. And definitely let me know if you have any questions or if you want some help. And I'll give you a hint. Instead of putting it in radical form, let's call this 2x cubed plus 3 to the 1/2 power. It's a little bit easier to take the derivative when it looks like this. So we want u to be the outer function. So in this case, u would be this exponent. It would be the 1/2 power. So it would just be, we don't really care what's on the inside. It would be just something to the 1/2 power. So then, of course, the derivative of that, we would just apply the product, or the power rule. We would make this 1/2 times all of this to the negative 1/2 power when we apply the power rule. All right, let's go ahead and review this problem together. So we have a general idea of what u should be, and we know exactly what v should be. So of course, the rule says we want to take u prime and then plug v into u prime. So if u is some function to the 1/2, that means that u prime is going to be 1/2 times all of the stuff we have on the inside. And then the power rule says we're going to take 1/2 minus 1, and we get -1/2. So we want to take this and then just plug v directly into the inner part of this function. So this would be 1/2 times v, which is 2x to the third power plus 3. And then we have to take the derivative of the inside, the derivative of v. V prime is going to be 6x squared plus 0. So we can put these two together. 6x squared over 2 is just 3x squared. And then this right here, we can just rewrite this so that it is 2x cubed plus 3 under the radical in the denominator of a fraction. So this would be square root of v. And that is our derivative. That is our g prime of x. Let's do a few more examples. Let's see what would be a good one. Let's say we have y is equal to square root of cosine of x. So we can see that the inner function is going to be cosine. The outer function is going to be the square root. So let's rewrite this. We'll make it cosine of x, and then that whole thing to the 1/2 power. So then y prime is going to have to be 1/2 cosine of x. And then this is going to be 1/2 minus 1, so -1/2. So we get 1/2 square root of cosine of x, but then we also have to take the derivative of the inside. The derivative of the cosine function is sine, or negative sine. So we have our first part times -sine of x. Move the negative out front, and we get this as our derivative. Now let's try one that's just slightly different. Maybe instead of square root of cosine of x, we'll make this cosine of 2x instead. So cosine is our outer function, 2x is our inner function. So y prime is going to be, well, the derivative of cosine is negative sine. So we're going to make it negative sine of 2x. And then we're going to multiply that by the derivative of the inner function. Derivative of 2x is just 2. So we could write it as -2 times sine of 2x. And yeah, that's it. That's the derivative for cosine of 2x. Let's see if there are more examples for us to try. Let's try this one. Let's take the derivative of 5 times the tangent of 2x plus 1. So we want to apply the product rule before we go any further. We're going to apply the product rule because this is u and then everything else is v. So it's going to be the derivative of the first times the second, and we don't even really need to write all that because the whole thing is just going to become 0. And then we have plus the first times the derivative of the second. So this is going to be v prime. So we want to use the chain rule. We're going to change the derivative of tangent. We're going to take the derivative of tangent, which is secant squared. I just want to copy this down off to the side. Derivative of tangent is secant squared. So this is going to be secant squared of 2x plus 1 times the derivative of the second. So it's going to be times derivative of 2x plus 1, which is just going to be 2. So this would be 10 times secant squared of 2x plus 1. All right, and that's it for today. If you don't have any questions, you're free to go. No homework tonight, but there will be on Thursday night. All right, I will see you guys later.